All right, put on your seatbelts, boys and girls. This is going to be a long and bumpy ride. I'll be as quick as I can. Before we talk about matrix multiplication, though, we have to talk about matrix addition. So if I have two matrices, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to add to that 3, 7, 8, 4, 12, 16, 8, 2, and 0, then all I do is element by element addition. The upper left-hand element, I add to the upper left-hand element, I get 4. The middle upper element, 7 plus 2 is 9. The 3 plus 8, see how they're in the same position in each matrix? 8 and 3 is 11. And then 4 and 4 is 8. 5 and 12 is 17. And I think I'm just going to finish out. 6 and 16 is 22. 7 and 8 is 15. 8 and 2 is 10. And 9 and 0 is 9. And so that's the end of it. That's all I do for matrix addition. No problem, easy peasy. Another thing that's very much like working in real numbers that has to do with matrices is scalar multiplication. So if I have the same matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to multiply that matrix by, say, the number 2, all I do is I multiply 2 times the first element to get 2, and then 2 times the second element in the first row to get 4. 2 times 3 is 6, and so on and so on. 2 times 4 is 8, 2 times 5 is 10, times 6 is 12, times 7 is 14, times 8 is 16, and 2 times 9 is 18. And that would be a scalar multiple. Now, I put these two together because we don't really have something like matrix subtraction. So let me name these matrices. Let's call this matrix A plus matrix B equals matrix C. In this case, I've got scalar K times matrix A equals matrix, well, I better not use C because it's different. A is the same, but this would be D. So I use a capital letter to describe my matrices. My scalar would be a lowercase k. All right, so now on to matrix multiplication, and we have to do a little bit of notation. First, we know that matrices are made up of rows and columns of numbers, and so when we describe the size of a matrix, we always describe it as the row size by the column size. Okay, so that's the size or the dimensions of a matrix. Also, in any matrix, the elements are always listed as the same letters. So for this matrix, uppercase A, we would use a lowercase a. You don't have to, but it helps keep the record keeping clean and tidy. So if I had a matrix AAA, 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 I need a way to distinguish the fact that this A is actually a different value than this A, because we can see that we don't have all the same value in our matrices. And so we follow the same convention of row by column. We call this element the first row, first column element, so the A11. This element is in the first row, second column, so we call that A12. A13, I mean, it's very simplistic. A21, A22, A23, a third row, first column, third row, second column, and third row, third column, and so on. If the matrix was bigger, we would just keep adding elements of either numbers for the column or numbers for the rows or both. And so we identify the location of an element in a matrix by row and column. Lastly, when we multiply matrices, if you have a M by N matrix, meaning there are M rows and N columns, and you want to multiply that, this inside number, if you multiply that to another matrix, this other matrix has to have an N here, N by, for example, P. the row of the first matrix has to be identical in size to the column of the second. Let me reverse that. The column of the first matrix has to be identical in size to the row of the second matrix. So these have to be the same number. If you write them side by side, that inside number has to be the same. And then informationally, the result of multiplying two matrices together will give you an M by P matrix as an outcome. So let's do an example. So I'm given matrix A equals 4, 1, negative 6, the first column, 5, 9, negative 3 in the second column, and B is 7, 0, 1 and 2, 6, 8. All right, so first, and I'm asked to find A times B. Okay, so find the value of A times B. Multiply a matrix A to B. All right, well, first, before I can do that, I have to determine whether it's even possible, right? So A is a 3-row, 2-column matrix, so it's a 3 by 2 matrix. B is a 2-row, 3-column matrix, so it's a 2 by 3 matrix. These two are the same. So I'm good to go, and I know that my outcome is going to be a 3 by 3 matrix, and I'm going to make use of that to help me with the manipulations that can be a little bit tricky. So since I know I can multiply them, I'm going to rewrite it. 4, 5, 1, 9, negative 6, negative 3 times 7, 0, 1, 2, 6, 8. And I know that my result is going to be a 3 by 3. So I'm going to have one row. I'm going to have an element in my outcome, in my C matrix. Let's say find A times B equals C. Find C. So my C matrix is going to have an 3 by 3 configuration, so I'm going to have a row 1, column 1. I'm going to have a row 1, column 2, and a row 1, column 3. I'm going to have a row 2, column 1, 2, 2, and a 2, 3. And I'm going to have a row 3, column 1, 3, 2, and a 3, 3. So I know that my product matrix is going to have that configuration. And now I'm going to use these addresses. So notice I wrote the addresses down, right? I wrote the addresses down because I'm going to use those to help me when I do my multiplications, or when I do my multiplications. So here's what I want to do. I want to multiply the first row of the first column to the first the first row of the first matrix to the first column of the second matrix. I'm going to multiply the first row of the first matrix to the column of the second matrix. Okay, I'm going to actually erase that because you have to get into the habit of seeing it without marking it up, because you'll see in a minute that you'll be constantly erasing those marks. So we're going to do it element by element. If it's the first row and the second column, I'm going to take the first element and the first element. So I'm going to do 4 times 7, and then I'm going to do 5 times 2. Okay, so 4 times 7 is 28, plus, add them, 5 times 2 is 10. So that's going to be the value of that first element in my product. Next, I want first row, second column. First row, second column. 4 times 0, 0 plus 5 times 6, 30. Okay. Next, first row, third column. I'm still using 4 times 5, but now I've moved over to my third column. 4 times 1 is 4 plus 5 times 8, 40. Okay, let's move on. Second row, first column. Second row of the first matrix, first column of the second matrix. 2, 1. 2, 1. 1 times 7 plus 9 times 2. Keep going. Second row, second column. Second row, second column. Element by element. First to first is 0 plus second to second. 6 times 9 is 54. Second row, third column. Second row, third column. 1 times 1 is 1 plus 9 times 8, 72. Okay, let's do third row, first column. Third row, first column. Negative 6 times 7, negative 42, plus negative 3 times 2, negative 6. Third row, second column. Third row, second column. Negative 6 times 0, 0 plus negative 3 times 6, negative 18. And last but not least, third row, third column. Third row, third column. Negative 6 times 1 plus negative 3 times 8, negative 24. Okay, now I can just put them together because it's simple addition. 28 and 10, 38. 0 and 30, 4 and 40, 7 and 18, 54, 72, 73, negative 42 minus 6, negative 48, 0 minus 18, minus 18, and negative 6 and negative 24, negative 30. All right, so now let's multiply B times A to see if we get the same thing. Are matrices commutative? I'm not sure, but let's see. Well, first I have to determine if I can multiply B times A. So B is 701,268, and A is 4,1, negative 6, 5, 9, negative 3. So we're looking at a 2 rows, 3 columns, 2 by 3, and a 3 rows, 2 columns. Good, I can. So 3 by 3 is on the inside. That's the same, so I'm good to go. And I'm going to get a 2 by 2 when I finish, which is kind of convenient because it's a very tiny little matrix. So a 2 by 2 means I'm going to have a 1, 1, and a 1, 2, and a 2, 1, and a 2, 2. So 7 times 4 is 28. Row 1, column 1, row 1, column 1. 7 times 4 is 28, plus 0 times 1 is 0, plus, notice I keep going element by element. The first to the first, and then the second to the second, and then the third to the third until I run out of them. So I have 1 times negative 6, so that's a negative 6. All right, so now no more of this greening it up. First row, second column, first row, second column. 7 times 5, 35. 0 times 9, 0. 1 times, whoop, I got lost. First row, second column. 7 times 5, 35. 0 times 9, yes. 1 times negative 3 is a negative 3. All right. Second row, first column. So 4 times 2 is 8, plus 1 times 6, 6, plus 8 times negative 6 is negative 48. And last but not least, second row, second column. 2 times 5 is 10, plus 6 times 9 is 54, plus 8 times negative 3 minus 24. Put it all together. 28 minus 6, 22. 8 and 6 are 14. 48 take away 14. Oof, let's see. So that's negative 38, 32. 35 take away 3 is 32. And 10 plus 54 is 64. Take away 24 is 40. Done. So they're not commutative. Notice A times B does not equal B times A. The order that you multiply matters for a matrix. This is super important. And last but not least, there are some properties for matrix multiplication. Let's see if I can squish them up in here. Well, I better not. So properties. So suppose you have three matrices, A, B, and C, and you have one scalar K. All right, and we're required, I'm not going to write this down, but I'm going to write the properties, but it's expected that all of the product definitions apply. So in order for this to be true, they have to match the 2 by 3, the 3 by 2. So if they're multipliable, right, if you can multiply them together, then all of these properties hold true. So we have an associative property of matrices, and they happen to, it happens to look just exactly like the associative property of multiplication of real numbers. If you want to multiply A times B times C, it doesn't matter if you multiply B times C first and then A, or if you multiply A times B first and then C. So the associative property. Same thing with the scalar, associative, A-S-S-O-C, associative property of scalar multiplication. If I have a scalar times A times B, I can either multiply the scalar times A and then multiply B, or I can choose to multiply the scalar times B and then multiply by A. So it doesn't really matter which way I multiply first for scalars. There's a left distribution property. And the left distribution property says that if I want to multiply a matrix times the sum of two matrices, that it's okay if I distribute, right? So I can multiply C times A and then multiply, I don't like that C, sorry. Then I can multiply C times B, and I can add those results together. So it's a distribution property for matrices. It works whether you're distributing from the left or from the right. A plus B, add two matrices together and then multiply by C is the same thing as multiplying C times A and then adding C times B. And that is enough for today.